Smart contracts have limited access to information and can only see data as it exists in the present moment. Brevis expands this vision to include historical data, and it does this with a trustless ZK mode as well as an efficient optimistic mode. In this video, I'll explain how these systems work. Note, this video was made with support from Brevis, but my goal here is just to explain these systems, not endorse them, so do your own research, not financial advice. I'll explain Brevis and the rest of this diagram here in a second, but first let's review the problem that we're trying to solve here, which is this limited data access for smart contracts. And to do that, I want to zoom in on this part of my diagram here. And this is meant to be a representation of the Ethereum world state. And if you're not familiar, the Ethereum world state is just a set of all of the accounts and contracts in the whole system. So all of that data. So for every account, which I'm representing as these narrow rectangular sections of data, every account has address pointing to a balance and a nonce. Every contract, which I'm representing as these larger sections with some color in them, they have address pointing to balance and nonce, and then code and storage. And so this data is really the core central data of Ethereum. Like, this is kind of what the whole system exists to support, is this world state and the changing of that world state as a result of transactions, right? So this is the central thing. And anyway, in this world state, we have our contracts, and these contracts have access to, I would say, 4 main categories of data. So the first and most obvious is that these smart contracts have access to their own storage, right? They can read and write from their own storage. That's pretty obvious. The next would be that contracts can read and write to the storage of other contracts, but only in a limited sense, because this contract, for example, it might make a call to a function on this contract, and that function might go fetch something from storage and return that value to the original contract. But that can only happen if this second contract has made public some function doing that, right? By default, the storage here cannot be read by another contract. It can only be read if there is some function granting explicit read access, right? And it's similar for writing to another contract storage. Like, a contract certainly cannot arbitrarily read or write to some other contract storage, but if there's a function that it can call which makes some changes to, that contract's storage, then it can, in that sense, affect the storage of another contract, right? So anyway, those are the first two. The next would be that when a transaction is created, the user can, inject some data into that transaction as call data, and, send that to a contract, and the contract might do whatever it does with that data. So, for example, an Oracle contract might, someone might send to an Oracle contract a transaction which has call data specifying the price for some stock on that day or something, right? Information that is outside of this realm, this little universe. And so that's a way that new information can be injected into this realm. And the fourth, I would say, is that when a contract is deployed, something similar can happen. New information can be injected and kind of bundled into the deployment of that contract. So for example, if you deploy a token contract, you might include a whitelist, and there's some addresses there. That's new, fresh data coming into the system. Anyway, all of this data that a contract can access, these 4 categories, these are all happening in the present moment, in a sense, right? Like, smart contracts cannot see history. So when they're reading their own storage or the storage of another contract, they can only see that storage as it is at that point of execution. When that transaction is happening, they can see this universe as it is at that point. They can't say, like, okay, what was my storage value 10 blocks ago for this storage, this variable? And they can't see, for another contract, they can't say what was the value a year ago or when this contract was deployed or anything like that. They're trapped only in the present moment. And what Brevis does is it expands this vision, so to speak, so that contracts can see they're not confined to the present moment. They can see through history. They can see through time. And so what that allows, and here's my visual metaphor of that. So if we imagine, you imagine there's this Ethereum world state, it's all the accounts and contracts. And for each new block, we have some modifications to that world state. So we have a new kind of snapshot of the world state. So we can imagine then this like stack of world states through time, right? For each block, we get this new stack or a new snapshot. So then the entire history of the system is like this big stack, right? So anyway, what Brevis allows is for a contract to see through this stack, to see through time. And the other thing that Brevis allows is for seeing through the blockchain. Because the other thing is that smart contracts, they cannot see the contents of a block. Like you can't have a smart contract, executing a transaction and then going and saying, okay, in the previous block, grab the first address of the first transaction, the sender address of the first transaction. You can't do that. Even in the current block that transaction is in, that is being executed, you can't look through the block. Like you can only see your own transaction, your own call data, and like the RANDAU value, and a couple little things, but you really can't see through the block. So Brevis allows for this as well, the ability to query through the blockchain history, right? So that's what we unlock here, is seeing through history of the world state, the state of all of these contracts, and querying through that history, querying through the blockchain. And finally, Brevis allows for seeing into other blockchains. So if this is our little universe and we're gaining the ability to see through time in this universe, then Brevis also gives you the ability to see into other universes, other blockchains. So with that capability, there's just a whole expanse of things that we can potentially do with that. So how does all of this work? As I mentioned in the intro, there's two modes. There's a pure ZK mode and an optimistic mode. I'll explain the pure ZK mode first because it's simpler. So suppose you're this contract here and you want to do a query through the blockchain history, perhaps looking through the last 100 blocks and finding the top 3 transactions which make the largest buy of your token, right? That could be a useful thing to know. So you want to do that, and the way you do that is that you're going to, as this contract, emit an event. The event will contain a query specifying what you want to do, looking through those 100 blocks. And that query is going to be picked up by a Brevis node, who will then fulfill the query. They're going to look through their own copy of the blockchain and, look through those 100 blocks, do the computation and calculation, and ultimately produce the result. And then what they're going to do with that result is generate a ZK proof of the correctness of that result. They're going to prove that given that query, this is the correct result using the official true blockchain history, right? And then they're going to take that query result and proof and send it to Ethereum, where the proof will be verified by a contract on Ethereum. And then finally, the original contract can use that result. They can see that the proof has been verified, and therefore the query result must be correct, and they can confidently do whatever they're going to do with that information, right? Now, this approach is great, and it works fine, and it's trustless, which is awesome. But the downside is that you're generating a ZK proof for every query, right? And that just imposes or creates a certain amount of cost and friction, right? ZK proofs can be expensive to generate, especially if you're proving over a huge amount of data. So that's just it's a bit of a point of friction, or it adds some additional cost. So the alternative is that we have this optimistic mode, and I'll explain how this works in a second here, but the main idea is that instead of having a ZK proof for every query, we're going to potentially have 0 ZK proofs in the best case, and in the worst case, just a few. But we're still going to have a very high degree of confidence that the queries are being fulfilled correctly. So this optimistic mode takes principles from optimistic rollups, hence the name, and we optimistically assume that the query is going to be fulfilled correctly. So we optimistically assume that the nodes are going to be honest. And the reason we can do that is that there's high economic penalties for dishonest behavior. And this dishonest behavior is also very easy to detect. Like, it's very easy to see when a query has been fulfilled incorrectly. And it's very easy to prove that that has happened. And therefore we can impose economic penalties on the dishonest node, right? So because there's this clear economic penalty, it's easy to detect, it's easy to prove when a fraud has happened. It's kind of crazy and highly unlikely that these nodes are ever going to be dishonest, right? And of course they have on the other side, they also have their economic incentives to be honest, right? They get rewarded for being honest and punished for being dishonest. So suppose you're this contract here and you want to query through the world state history. Maybe you want to look at some ERC20 token contract and see how the token holders have changed in some specific way over the past day. So what you'll do is you'll emit an event, and that event will again contain a query. That query will be picked up by a Brevis node, who is then going to fulfill the query. They're going to look through their own copy of the Ethereum world state history, do the computation, and figure out the result. But instead of producing a ZK proof for that result, we're going to take the result and query and put that information into this Brevis proof of stake co-chain, this separate blockchain, which exists to support this functionality that I'm describing here. So that node is going to put the result into this chain, and they're going to attest to the correctness of the result. They're going to sign off on it, right? They're going to digitally sign that message, and they're going to, in doing so, they're going to be putting some of their economic backing behind that result. And, right, they're saying basically like, I'm going to put some money on the line that this is correct. And then, of course, what the other nodes in this proof of stake network do is they're going to check that work, recompute the query to ensure that it's correct, and then they themselves are going to sign off on it as well if it is correct. And when they do that, they are putting their economic backing behind it as well. So what happens is that if the query was done correctly, most or all of these nodes are going to sign off on it, add their signatures to the query result pair, and they're going to add their economic backing behind it. So that's what I'm drawing here. These blue squares are meant to be restaked ETH, and you can see that each of these nodes is sending a little chunk of that restaked ETH to this proposal, this query result pair, and they're putting their economic backing behind it. Now, of course, what that allows for us to do is that we have the signatures of all of these nodes signing off on some result. So now if we find that this result was fraudulent or incorrect in any way, we can slash them, right? And so that is what I'm depicting here. So here I'm imagining that this proposal was done incorrectly, that there has been some fraud, and the result that's given here is not correct. So here we have this watcher node who's been just observing this chain and double checking the work. And this watcher could be any machine run by pretty much anyone. It could even be one of these nodes here who wants to, keep the system honest and perhaps win some money for themselves. So anyway, this watcher node is going to be watching these proposals. It sees that this one is fraudulent. And what it's going to do is generate a ZK proof of this incorrectness. So it's going to say, here's the query, here's the result that was given, but that's wrong. Here's the correct result, and I'm going to generate a ZK proof of that in fact this is the correct result for this query, and send that to Ethereum. A contract will verify the proof. It will see that the true result does not match the result that was given here, and then it will slash any of these nodes who signed it, right? Any of these nodes who signed off on this, they're going to be slashed. So the ETH, the restaked ETH, which these guys put backing behind this proposal, is going to be slashed, right? And of course, the watcher is going to win some of that ETH. So they're going to be rewarded for their effort because, of course, generating a ZK proof costs some money, some computational work, and so they need to be incentivized to do that. And yeah, so these nodes will be slashed. So of course, what that does is, just like in optimistic rollups, having this whole scheme set up, it keeps these nodes honest, right? They have this undeniable record of what they've attested to, and if they've attested to something false, there's this window of time, which is, large enough for watchers to detect the fraud, generate the proof, submit that to Ethereum, and ultimately have these guys lose their money. So of course, all of that has the effect of keeping this thing honest. So again, instead of having to generate a ZK proof for every query, we now have the situation where we probably don't have to generate any ZK proofs, or very few of them, and yet we still have this high degree of confidence that things are going to be done correctly. Now, before I explain these challenge periods, I want to point out that this optimistic mode actually has a fundamental advantage over the ZK mode, beyond just the fact that it's more efficient, that we don't have to generate a ZK proof for every query. There's also something that this optimistic mode can do that the ZK mode can't really, and that is proofs of non-existence, or proofs of completeness of a set. So what I mean is, for example, if you wanted to prove that some specific address has never interacted with some specific contract, that would be very hard to prove with a ZK mode. Because what you would have to do is you would have to take all of the possible range of data, like perhaps the entire chain history, and do a proof over all of that data, proving that, user A did not interact with contract X, right? And with that amount of data, that can just be practically infeasible. But in this optimistic mode, that's actually really easy to do, right? You have the query, and some node fulfills it, so they look through the whole history. And that might be a little bit of work, but it's not that much. So they see that this user has never interacted, this address has never interacted with the contract, so they can produce the result and say, correct. And then if they are lying, it's very easy to prove that. Because if they are in fact lying, and this address did in fact interact with this contract, it's easy for a watcher to prove that. They just find the interaction, right? They just say in block Y, here's the transaction, here's the hash, et cetera, and generate a proof, put that on chain, boom, right? It's done. So that, of course, again, keeps these guys honest, and therefore we can fulfill these kinds of queries. We can look for this sort of, or achieve this proof of non-existence of some event. And in a similar sense, we can also achieve these proofs of completeness of a set. So let's say you wanted to obtain the set of all, or all of the addresses who have been in the top, 10 token holders for some contract, right? You just want that list. Now, again, to generate a ZK proof of this, you would have to do the proof over the entire range of possible blocks and history that could have happened in, which is infeasible. Here, you just generate the set. The node fulfilling the request just looks through, grabs the set of those addresses, and then the watcher, if they see that an address has been left out, it's easy for them to prove that, right? So this is kind of a fundamentally new thing or different thing that we can get from this optimistic mode. So now I want to explain these challenge windows, and you'll see beside my proposals in each of the blocks, each proposal has these two little health bars, right? And these are meant to represent these two different challenge windows. So as you can see, these health bars basically deplete as time progresses. So the most recent block has these proposals with full health bars, and then they deplete and eventually hit 0, at which point these proposals are frozen. Like, they're considered final, and the challenge window has passed, the capital is freed, and that's it. So easier to understand challenge window is the larger one. This is the system defined challenge window. And this is the big health bar. And this one is pretty simple. It's like a few days long, and that defines, this challenge window defines the period in which you can challenge a proposal and potentially prove fraud and win some bounty and have some slashing happen. So that's basically pretty simple. That's how it works. It lasts a little bit of time and then it closes and the capital is freed. And so just on that note too, like something that's really interesting to think about here is when we think about these, this challenge window and a certain number of proposals that are sort of live or in the air or active or whatever you want to call it, you can then think about this notion of like economic bandwidth, right? Because when we think about, you know, these nodes having a certain amount of capital available, right? And then we have this window which lasts a certain amount of time, say 3 days, and we have some number of proposals that are alive in this window, this, you know, continually sliding 3-day window. Let's say it contains, for ease of math, just 100 proposals at any given time, right? We can then take the total amount of capital these nodes have available, and we're basically dividing that capital over those 100 live proposals, right? So if these nodes have 1,000 ETH between them, then each proposal in this example would get 10 ETH, right? That's the most backing that that would be the average backing that these proposals could have, right? And so then, of course, like you can think about this economic bandwidth where if these nodes had twice as much capital, you could either double the economic backing for each proposal on average, or you could double the amount of proposals that are live in your window, right? So there's this notion of economic bandwidth, which is, it's interesting, right? And of course, that's one of the reasons you need to have this window that closes at some point, is because if this window, this challenge window lasted, you know, like 6 months, then you're spreading out this capital over a huge amount of time, and you're going to spread it very thin, right? So you're not going to be able to handle the throughput. So there's a trade-off there between, you want the window to be long enough such that a ZK proof can be generated if there is some fraudulent result given, but you don't want to go so long that you're spreading your capital too thin, right? Now, in addition to this system-defined challenge window, which is a few days long, we also have this, generally speaking, shorter user-defined challenge window, which can be as little as 30 minutes or even less. And the purpose of this smaller challenge window is that this is the amount of time that the app, which originally kicked off the query, is going to wait before using some result, right? So they're going to kick off the query, some node is going to fulfill it and put it into a block, into the cochain, and then the app, the DeFi app or whatever that kicked off this whole thing, it's going to wait 30 minutes before using that query, before proceeding with that result. And, you know, the reason we have this window that's smaller potentially than the wider one is that, you know, an app doesn't necessarily want to wait the full 3 days before proceeding with some result, right? That's just too long. And so there's a trade-off there where they want to wait a little bit of time to allow for a challenge to be initiated, right, in case there's a fraudulent result, but they don't want to wait forever. They don't want to wait the full 3 days necessarily. So if they want to have really high confidence in the result, they may in fact wait the full duration or a day or something. But if it's not totally mission critical, they might wait only 30 minutes or so. And, you know, when I first learned about this, it was a little bit confusing because I couldn't quite understand why you would have this short window. You know, like let's say you have a window that's 10 minutes long. It's like, okay, what's the point of the wider window? After that 10 minutes has passed, then what's the point of the wider window? Like you only have 10 minutes of security, so to speak. But it's not quite like that, because from the perspective of these nodes, even if some app was saying, here's my query, and I don't care about any user-defined challenge window, it can be 0. I'm going to use the result as soon as they're posted. You know, if you're one of these nodes, you might think, okay, that means I can post some fraudulent result. They're going to proceed with that computation, and I can get off scot-free. But that's not the case. You still have this wider window where some watcher will still most likely create a proof that you've lied, and you'll be slashed, right? So even if that challenge window, the small one, is 0, yes, the app may proceed with that result and the result is incorrect, and they do some transactions or computations. But as one of these nodes, you're still going to get slashed, right? People are going to see that you lied, and you're going to get slashed maybe an hour later, but you're still going to get slashed. So there's still a strong incentive for you to be honest, right? And so, yeah, these two challenge windows allow for, this wide window, which keeps all of the results honest, which gives plenty of time for the watchers to detect fraud and prove it. And then the shorter window does have some impact on like the confidence of the results, but you still have this wider window kind of enforcing honesty to a high degree on all of these results, right? Okay, so a little more details about this challenge process. The way this actually works is that the challenger, when they see some proposal which is incorrect or fraudulent, they can initiate the challenge before having to submit the ZK proof. So they initiate the challenge, which notifies the system that this proposal is being challenged and that it may be fraudulent. And what that does is it allows for the app, which kicked off this whole thing, it allows for them to potentially wait a little bit and not proceed with the results that have been posted and see what happens with this challenge, right? And so the advantage of doing this is you don't really want the watcher to have to detect the fraudulent proposal and then generate the ZK proof before the system really knows what's going on, right? Because that ZK proof could take some time to generate. So you might have a proposal which has a user-defined challenge window of like 10 minutes, but maybe the ZK proof takes 15 minutes to generate. So then the watcher is sitting there like, I can clearly see this proposal is false, but I can't really do anything about it until I have the proof. The proof takes too long, so then the app is proceeding with these incorrect results. So instead, you just have this initiation. The challenge initiation can happen, right away. And then we have a bit of time to generate the proof. Now, the amount of time, so first of all, when a challenger does this, kicks off this initiation, they have to put up a bond, right? So they have to put some skin in the game and put up a little bit of capital, because you don't want them to have no consequence for initiating challenges that are not legit, right? You want to, because if they could do that, they could just grief the system and continually do that, and it wouldn't work. So instead, they have to put up a little bond, and if they fail to submit the valid ZK proof after the duration has passed, then they lose their bond, right? And so yeah, the watcher has a little bit of time to generate the proof. Also, the bond, the amount of time that they're given to submit their proof and fulfill this initiation, that amount of time is proportional to the bond. So if they want to buy themselves more time, they have to put up a larger bond. And that also makes sense, because if you're, asking this app or whoever to wait for like hours for your ZK proof, it kind of makes sense that you would need to pay for their time, right? Put up a larger bond and buy yourself some more time. And of course, if you are being honest and there is in fact, the result is in fact fraudulent, then it's going to be fine anyway, right? You'll get your bond back and you're going to win the bounty, and so it should be totally fine. Now, the other thing that is kind of good about doing it this way is that if you were waiting, like if all of these watchers had to race to compute and generate the ZK proof of the fraud without any challenge initiation step, then you would have the situation where potentially like dozens of nodes are all racing to generate a ZK proof. They're all duplicating that work, right? And then only the first one to complete the proof wins the bounty. So then all these other nodes are like wasting computational work, right? So it's better to have a race to initiate the challenge, and then you just allow for the proof to be generated, right? You're not duplicating that work. And also, it's a very good thing that there's this race, there's this time pressure, right? One node wins the bounty, right? If they see a fraudulent proposal. So that creates this time pressure, which is really good if you're one of these apps, because you, of course, if some proposal is being made, some result for your query, if that thing is incorrect, you want to know as fast as possible, obviously, right? So the fact that there's this race to win the bounty, this race among the watchers, that creates this incentive for that challenge to happen as quickly as possible, which is a good thing. One more detail I'll mention is that apps can also set their crypto economic threshold that they require for some proposal to be accepted into the chain. So they might want 90% of the nodes, 90% of that capital, to sign off on the result for their query before they accept it, before they want it to be accepted into the chain. Or they might only need 10%, right? And this is, of course, is going to vary depending on the use case. And so this is a little bit like how proof of stake works in general, where for a block to be considered part of the canonical chain, you need a certain number, a certain threshold of validators to sign off on it. And it's a similar thing here, except rather than having a fixed threshold for every block, here it's like each sort of transaction, each proposal within the block can have its own threshold, which is pretty interesting. So anyway, that is basically how the optimistic mode works. And so, yeah, in summary, we have this capability for smart contracts to see through history, see through time, see through the blockchain, and also to see to other chains entirely, and query against all of this information. And Brevis provides two modes to do this. There's the trustless ZK mode, which is, rock solid, but a little more costly in terms of proof generation. And then you have this optimistic mode, which is super efficient and, should have a pretty high level of security as well. And also has these extra capabilities, like I mentioned, the proof of non-existence and proof of completeness of a set, et cetera, et cetera. So I think it's a pretty interesting unlock in terms of what contracts can do. They now have access to a huge amount of data, and we'll have to see what people come up with, right? What use cases developers can imagine. Okay, thanks for watching. I hope that made sense. If you have any questions or comments, leave them below and I'll try to get to them. And yeah, I have some exciting videos on the way, so watch out for those. And yeah, thanks for watching and see you next time. Peace.